Welcome to the Explainer. Today, we're stepping into the incredibly high stakes, but honestly largely invisible world of electric vehicle battery safety engineering. We all see the shiny exterior of an EV, but right under the floorboards is this amazingly complex ecosystem that's constantly fighting to keep immense amounts of stored energy perfectly stable. We're going to unpack exactly how engineers prevent catastrophic failures long before they even have a chance to begin. Picture this for a second. You're driving your EV down a really long, steep mountain road. You're riding the brakes, right? Well, that means your car is aggressively using regenerative braking to slow down, literally pumping massive amounts of energy straight back into the battery. The electrical pressure on the individual battery cells during this is absolutely immense. So, if a cell gets too full, what actually stops it from overloading, overheating, and ultimately catching fire? Okay, let's dive into this. We're going to look at 5 distinct layers of defense today. 1. Root cause analysis. 2. Dual defense architecture. 3. Key prevention in design. 4. Strict process controls. And 5. Extreme pre-production validation. All right, Section 1, Root Cause Analysis. Let's take a look at the actual anatomy of a battery failure. The specific fault we're zeroing in on today is called P0DE7, which is a highly technical way of saying cell overvoltage or a balancing open circuit fault. Inside your battery pack, individual cells have to be balanced. When a passive balancing circuit fails, say a tiny microresistor burns out or a MOSFET switch just gets stuck open, that specific cell can't bleed off its excess power anymore. Over months of driving, that cell becomes dangerously out of sync. And during that long downhill charge we just talked about, its voltage can skyrocket right past safe limits. And this can build into a terrifying 3-stage cascade failure. Step 1 is the trigger. Maybe a microscopic metal splash from ultrasonic welding at the factory pierces a cell separator. Step 2, the chain reaction kicks in. The battery management system basically overloads its passive balancing circuit trying to compensate, which burns out the resistor. Then step 3 is the disaster. That intense heat melts nearby cooling tubes, leaking liquid coolant directly onto high-voltage copper bus bars, and boom, you get a total insulation breakdown. This right here is exactly the nightmare scenario engineers have to prevent. Moving to Section 2, Dual Hardware and Software Defense, or as it's often called, the Swiss cheese safety net. To stop that cascade failure dead in its tracks, engineers implement an ASIL-D graded architecture. Now that's the absolute highest safety classification in the automotive industry. Think of it like a flawless Swiss cheese safety net, where the holes just never align. What's really interesting here is the contrast between the software layer and the hardware layer. If the smart software sees the voltage hit exactly 4.25 volts for 1.68 seconds, it triggers a disconnect. But hey, software can glitch, right? So an independent hardware analog comparator sits there as the ultimate backup. If it detects extreme voltage, it bypasses the software entirely and physically snaps a rigid fault pin, instantly severing the connection, no questions asked. But get this, the system doesn't even wait for an emergency to happen. It's constantly diagnosing itself using built-in self-tests. Even when your car is totally turned off and asleep in your garage, it briefly wakes itself up, kind of like a parent checking a baby monitor, just to ensure no circuits are stuck in a state of self-discharge. And if things start running a little too hot while you're driving, it uses progressive power derating to automatically shift the braking force from the regenerative battery charging over to your traditional mechanical brakes to keep you totally safe. Let's look at Section 3. Key prevention in design. This is where we get into DFMEA measures. I really want you to take a look at this number, 9. In the engineering world of DFMA, which stands for Design Failure Mode and Effects Analysis, a 9 is literally the highest possible severity rating you can get. This is the exact rating assigned to the thermal runaway risk caused by cell overcharging. Because the stakes are a level 9, the physical design failsafes simply have to be absolutely uncompromising. And because of those massive stakes, the physical failsafes are brilliant. First off, every single balancing circuit gets its own independent microscopic PTC thermal fuse. If a switch ever gets stuck and overheats, this tiny fuse just melts and physically severs the connection before the circuit board can catch fire. On top of that, the cell separators themselves are shielded in a high-strength aluminum oxide ceramic coating that's specifically designed to prevent any of those microscopic metal splatters from piercing them in the first place. All right, Section 4, Strict Process Controls. This is all about flawless manufacturing. Because, let's be honest, a perfect design means absolutely nothing if it isn't built perfectly, right? This side of things is governed by PFMEA, or Process Failure Mode and Effects Analysis. On the assembly line, there is a strict, and I mean strict, zero-tolerance policy. We're talking 100% dynamic monitoring and automated visual inspections for every single board that passes through the factory. There's just no such thing as good enough when it comes to high-voltage EV batteries. So what does zero tolerance actually look like on the factory floor? Well, factories use online monitoring of the soldering reflow temperatures so that absolutely no tiny cracks form in the ceramic components. They use dynamic monitoring to ensure zero static electricity damages the super-sensitive microchips. They literally use 3D visual checks to verify that an automated vacuum conformal coating perfectly seals the vulnerable pins from any ambient moisture. And finally, at the end of the line, 100% of the switches undergo a dynamic voltage drop test to prove they operate flawlessly before they are ever allowed to leave the factory. Finally, Section 5, Extreme Pre-Production Validation. Welcome to the ultimate torture test. Long before mass production even starts, the system has to survive DVPNR, the Design Verification Plan and Report. Engineers subject these battery management boards to a matrix of 4 brutal extreme tests. They inject artificial overvoltages, they deliberately short-circuit the board, they bake it in extreme heat, and they subject it to intense moisture over hundreds of hours. Remember this super specific time limit from earlier? 1.68 seconds. In the very first test, engineers suddenly inject a highly dangerous 4.30 volts directly into the system. From the exact microsecond that voltage hits, the hardware fault pin has to trigger, and the main charging relay must physically snap open in strictly under 1.68 seconds. Not a millisecond later. It's incredibly fast. But how does the system handle direct physical damage? Well, if engineers manually short out a switch during testing, the system must detect it in just 100 milliseconds and permanently lock the battery from charging past 50% capacity to keep it stable. And if they force it into a permanent overheating state inside an 85 degrees Celsius oven, that tiny PTC microfuse we talked about earlier must melt perfectly, keeping the maximum board temperature strictly under 120 degrees Celsius. Zero charring, zero smoke, just total safety. The final hurdle is proving it can survive the actual life of the car itself. These boards are locked in a chamber for 500 grueling hours at 85 degrees Celsius and 95% humidity. Engineers even drip artificial coolant onto the chips with a live 5-volt current running through them to actively try and force a short circuit. To pass this, electrical leakage has to remain under 1.0 milliamp, insulation resistance must hold massive thresholds, and absolutely zero microscopic metal growths, which are known as tin whiskers, can form between the pins. Taking a step back and looking at this entire explainer, it's kind of breathtaking, honestly. To prevent just a single fault code, P0DE7, from ruining your car, there are millions of microscopic calculations happening behind the scenes, backed up by rigid physical failsafes designed to literally melt and break just to protect you. And it's all born from a design and manufacturing process that accepts absolutely zero compromises. Which leads me to this final thought for you. The next time you're driving down a mountain road, just casually tapping your brakes, think about the invisible war happening beneath your feet. Are we really just driving cars anymore, or are we piloting highly armored, incredibly sophisticated supercomputers? Stay curious and keep looking beneath the surface.